Oscillations. There's a lot we can say about oscillations. Uh, it'll be it'll be our subject matter for the next few days. Oscillations can have all kinds of different causes, but they all have a few things in common. That they're all caused by some kind of a restoring force. Restoring force just means a force that is always pulling or pushing an object back to its equilibrium state. For example, you've got a little block here attached to a spring. The other end of the spring is attached to a wall, so this end of the spring doesn't move, but of course this end of the spring can move. And then if you push that block to the left, it squeezes the spring. And now that the spring has been squeezed, it's an elastic object, so it'll try to expand back to its original length, and in trying to expand, it pushes on this mass, and the strength of that push looks like this. The push, we call it a spring force. It comes from a stretched or compressed spring. It's in the opposite direction from the displacement. That is that this mass was displaced to the left, then the push from the compressed spring points the opposite direction, points to the right. When the mass is right here, the spring is neither stretched nor compressed. So in that state, there is no spring force. In fact, in that state, there's no net force. So when the mass is here, then the spring is at its normal unstretched, unsqueezed length. No force, so that's equilibrium. This we'll call the equilibrium point, or the equilibrium location for the mass. But now you can see how this acts as a restoring force. Whenever the mass is on this side of equilibrium, the spring is compressed, and that means it'll try to expand back and push the mass to the right. The mass is over here and being pushed to the right. That means it's being pushed back towards its equilibrium location. So that's what we mean by a restoring force. This force is trying to restore the mass to its equilibrium position and restore the spring to its equilibrium length. Let's think about what's going on here. Let's say I pushed the mass and now I let go. Well, there's a force acting on that mass, a force pushing this way. The only other forces on this mass are the normal force from this surface pushing up and then weight pushing down, and those two forces will cancel out. We know they'll cancel out because there's nothing happening along the vertical direction. There's no motion. In fact, there is constantly no motion. So a constant velocity along the vertical direction, constantly zero, means zero acceleration, so zero net force along this direction. The only other force besides those two vertical forces that cancel out is the spring force. So that, in this case, spring force just amounts to the same thing as net force. So net force on the spring points to the right, so the spring accelerates to the right. Newton's second law tells us that the direction of acceleration is the same as the direction of the net force that caused it. known ever since early on what the direction of acceleration means. The direction of acceleration tells you the direction of the velocity that is being added on to the motion. That is, acceleration going this way means as time goes by, more and more rightward velocity is added to the block. It's moving to the right and then having more rightward velocity added onto it, so it then moves even faster towards the right. In other words, as long as this force is pointing to the right and the block is moving to the right, it speeds up. That's just an example of something we've seen quite a few times before. The velocity is pointing to the right, and the acceleration is pointing the same way. Whenever velocity and acceleration point the same way, that corresponds to speeding up. Or to put it slightly differently, whenever the net force and velocity point the same way, that corresponds to speeding up. Well, eventually, we'll call this situation A, eventually the mass gets back to the equilibrium point. At equilibrium, the mass is not displaced away from equilibrium. The spring is not stretched or compressed. The spring is at its normal length. So this is 0. There is no spring force, and therefore there is no net force. No net force means no acceleration at that moment. But there, of course, is velocity at that moment. It's the mass has been speeding up ever since I let go of it and allowed it to start moving to the right. So it has speed at this point. If something is moving and it has no acceleration, it'll just keep on moving. That's what we know from Newton's first or second law. So it'll shoot past the equilibrium point. And then eventually, well, for a while, if it moves past the equilibrium point, it's still moving to the right, but now it's past the equilibrium point, so the spring is stretched. There's a displacement of the mass away from equilibrium to the right, or what amounts to the same thing. This end of the spring has a displacement to the right. This part of the spring is stretched to the right. And that means now there is displacement away from equilibrium, so there is a spring force, and the spring force always points opposite to the displacement. So displacement is to the right, so the spring force is to the left. In other words, net force is to the left. And acceleration always has to point in the same direction as net force, so acceleration is to the left. And we know that the velocity is still to the right now, acceleration is pointing the other way to the left. Whenever velocity and acceleration point in opposite directions, that always corresponds to slowing down. The mass is moving this way, but it's being pulled backwards by the net force, which is just a spring force in this case. And of course, if you're moving in one direction, but being pulled backwards, you have to slow down. Eventually then, the mass will slow down all the way to a stop. So that was situation C. And now situation D, it'll be the mass will have slowed down all the way to a stop. So zero velocity, but the spring is stretched as much as it's ever going to be stretched, because at this point it stops and it's going to turn around. So there's still displacement to the right, an even bigger displacement than at time C, so an even bigger spring force than at time C. But the spring force is still pulling to the left, because the stretched spring will try to snap back to its original shorter length, and as it tries to snap back, it's going to be pulling to the left, pulling on the mass. In this case, the spring force amounts to the same thing as the net force. So net force points to the left, acceleration points to the left. There's no velocity at this moment, but there is still net force and acceleration. They're at a situation that we'll call D. No velocity, but a leftward net force and a leftward acceleration means the thing is not going to stay at zero velocity for any length of time. Acceleration means when there's acceleration, that means the velocity is changing. So one instant after the velocity had this value, it's got to have a different value because it's accelerating, because it still feels a net force. And now acceleration points in the direction of velocity that is being added on. So it has zero velocity at this moment, but it's having leftward velocity added on, so it's going to start moving to the left. And as it moves to the left, it will have leftward velocity, and then still more leftward velocity added on. So let's look at that. So now, call this situation E. The block is now moving to the left. It's been gaining more and more leftward velocity because it has leftward acceleration. So moving to the left and acceleration to the left, once again, when velocity and acceleration point the same way, the object always has to be speeding up. And then eventually, it'll get back to equilibrium, and it'll be the same kind of situation as we saw earlier. The block is not displaced from equilibrium. The spring is not stretched or squeezed, so it has it has its normal equilibrium length. So there's no spring force, which means no net force, which means no acceleration at that moment. does have velocity to the left, and just like the other a half cycle earlier when the mass was moving to the right and passed by the equilibrium position, same thing. It's got velocity but no acceleration, which means it keeps moving with the same velocity. Keeps moving with the same velocity, so it doesn't land here or stop here. It overshoots this point and then starts moving to the left. And as soon as it does, it starts squeezing the spring. So now the mass and the right end of the spring are displaced to the left of equilibrium. So as long as things are displaced away from equilibrium, the spring will be either stretched or squeezed, so there will be a spring force. And as always, the spring force points opposite to the displacement. So the spring force is to the right, so the net force is to the right. So there's acceleration to the right. Acceleration to the right, while the direction of motion, the direction of the velocity, is to the left. And as we've seen before, whenever acceleration and velocity point in opposite directions, that always means the object is slowing down. Remember what's going on there. This is direction of acceleration is the direction of velocity that is being added on. So you've got leftward velocity, but you're adding rightward velocity to it. The rightward velocity that you add onto the original leftward velocity has the effect of canceling out, diminishing some of the leftward velocity. In other words, it keeps on moving to the left, but it's moving slower. So it keeps on moving to the left, but slows down until it eventually comes to a stop, and then it's in exactly the same state as it was at the beginning when I first squeezed the spring and then let go. So that takes us through one complete cycle of the mass's oscillation, and at every subsequent cycle, the exact same things will be happening to the net force and the velocity and the acceleration. It'll just keep on moving back and forth in exactly the same way. One thing to notice here, our net force in this case is nothing but the spring force, and that net force is then a restoring force, because it's always going to be either pushing or pulling the mass back to equilibrium. If the mass gets away from equilibrium, then there's a displacement away from equilibrium, and the force is always going to act to push it back. For instance, here, the mass is to the left of equilibrium, but the force is trying to push it to the right to get it back to equilibrium. Or here, the mass is to the right of equilibrium, so the restoring force will be pulling to the left to try to get it back to equilibrium. And it's that aspect of the force always pulling or pushing the mass back to equilibrium that's really the thing that causes the oscillations. Okay, and then you'll on the exercises you'll do a similar kind of analysis, but with a mass that's hanging vertically from a spring. So in that case, the the net force will still act as a restoring force. The only extra complication is that the net force is not just a spring force. The net force is going to be a combination of spring force and mass. But that combination will still act just like a restoring force.